good? Probably gonna run out of batteries again.
Still got
It's
half.
on 2 bars.
About half? Okay. Well, we'll get most of the review in here anyway. Okay, so basically this implies that A equals B equals C equals 0. Now, you ready to see what the world's most common mistake is at this point? I hope you don't mind, I like to show what the mistakes are because I don't want you to make those mistakes. I've just taught the class enough to know what people do wrong. What people will often do wrong at this point is they'll say, okay, good, A, B, and C are all 0, so my kernel of T is 0, 0, 0. That's what they'll say. And that's not right. Does anybody know what's wrong with saying that the kernel of T is equal to that? It seems like a reasonable thing to do. A, B, and C are all 0, so there you go, right? The problem is, when I write it like this is not a polynomial. This is not in my vector space V. This looks like something in R3, right? It's got 3 slots, right? So it looks like it's in R3. What you need to do, once you find out what A, B, and C are, you need to take those numbers and replace them back over into here, into your polynomial, to find out which polynomials are in the kernel. Well, if A, B, and C are all 0, then of course this quadratic polynomial just collapses to 0. So the right answer to this question would have been the set of just 0. The only vector that is killed by this transformation is the 0 vector. Actually, it turns out to be the definition of 1 to 1. But don't worry about that for now.
So that's the basis for the...
I didn't say basis. This is the kernel. It's a set of all polynomials that are killed by the transformation. Now I can ask you for a basis for the kernel. But the thing is, if this is the only thing in the kernel, then there's nothing to find a basis for, really. Actually, it's 0-dimensional. Right? So if I ask you for the dimension of the kernel, it's 0. The dimension of that kernel is 0.
Of that kernel.
For this example, on this problem, certainly is not always true.
Wait, so it's also asking for the basis, and so the basis would just be...
Find a basis for the kernel T. Yeah, there's nothing there.
So it's just
How did I say it in my solutions here? Probably just said there is no kernel. Yeah. See? Kernel T equals 0, which is 0-dimensional, and there is no basis. Yeah, so trick question. It's a trick question, basically.
Wait,
Okay.
so if there was supposed to be a basis, what would it look like? Would it just be...
What would happen? Okay. Right. Let's imagine that we work all this out, and instead of getting all the constants equal to 0, we get this system of equations, and we work it out, and we realize that there are some free variables or something when we back substitute it. So then in that case, maybe C would come out to be T, and B would be negative 5T. I'm just making this up. And A would be 8T, or something like that. Okay. Well, then when you write down what your kernel is, if this was A, B, and C, then your kernel of T would just be the set of 8T x squared minus 5T x plus T, such that T is a real number. It would just be all polynomials of that form. And what would be your basis then? Or how would you get your basis for that?
Set T equal to 1.
What did you say?
Set T equal to 1.
Yeah, or bust out the T is usually what I would say. Yeah, basically you bust out the constant, which is T, and you would just get 8x squared minus 5x plus 1. And that would be your basis, and it would be one-dimensional now. Because there was one free variable. That make sense?
Mm-hmm.
It's very important that your answer is a polynomial. The kernel and the basis for the kernel have to be from vectors from V. They have to look like polynomials. If you you write 8 comma negative 5 comma 1, you're not giving me a polynomial, you're giving me a 3 tuple, which is a vector in R3, and not what we're looking at here. That's it.
What did you say something about being one-dimensional because of the t?
This would be, if this was the problem, yeah, there's one free variable, which is t.
Right.
So after it's busted out, there's only one polynomial. This whole thing is just one polynomial. So it's a one-dimensional kernel. Okay. This ties up really closely with all the stuff from the last chapter. It's just, you know, we're adding this little definition of a kernel, but other than that, it's pretty much the same thing. Let's see, maybe before we do, there's also the range of the transformation. Let's do it now. Let's do it now. So I've got my formula over there now, so let's see, where do I want to go? Can I erase over here again?
Yep.
Okay, great. Guys, what you should do is definitely watch that video that I made about the kernel and the range of a transformation, because I do like 4 examples of each. And then come to class tomorrow night. We're going to do more examples of it tomorrow as well. So I think this will be, it's not that bad, it's just that you are having to kind of get it soaked up fairly quickly. So that's the only thing, try to focus on getting things down. Okay, the range. Here's my picture again. What we have over here in W is this huge output space. It's all the output. So W is M2 of R. The thing is, not necessarily every 2 by 2 matrix is actually an output. So you can transform every possible quadratic polynomial, transform every one of these guys, and you're going to, for each one, you're going to get a 2 by 2 matrix. But you might not get every 2 by 2 matrix as an output. That kind of makes sense? I can give you an easier example. This should make it really clear. Suppose that you just did, and this is a different, I'm not going to go into this too far right now, I just want to convince you right now that this W right here is not necessarily everything in W shows up as an output. Suppose that I transform a polynomial by taking its derivative. We actually showed that that was linear in class last week as one of our examples. Okay, if you go back and review those notes from last Wednesday, this is linear. But would you agree that when I take the outputs of this transformation, I can only get things that are cubic or lower? Because if you take a 4th degree, if you take an x to the 4th and you differentiate it, you're down to x cubed. So your outputs over here, the things you can get as answers on the right-hand side, is only part of W. W is all polynomials of degree 4 or less. You're only getting some of those vectors in W to show up as outputs. And so that's the reason that we have this other subspace called the range of T. The range of T is the set of all outputs that actually show up, right? It's the set of all transformed vectors. So you just take T of V for every vector in capital V. You just transform every vector. And it turns out that this is a subspace of W. And it may or may not be all of W. Pretty clear here with this example that the range of this transformation is not all of W, because you're only getting the possibilities for the derivative of a 4th degree polynomial are only going to be polynomials of degree 3 or less. You're not going to capture all of those 4th degree polynomials. The 4th degree polynomials, they are in W. but they aren't going to show up as the derivative of something. Because if you want to get a 4th degree polynomial as the derivative of something, you would have to have started from a 5th degree polynomial. Because remember, when you take derivatives, the power goes down. We don't have 5th degree polynomials here. So I'm not going to be able to hit. Basically, it's like this. These vectors go across. You take an input here, you know, v, here's t of v, right? So basically, all of these things you're getting here as outputs, that's the range of t. R and g of t is the range of t. It's not all of w necessarily. It might only be some of w. There could be vectors in w up here that are not on the receiving end of this transformation. Okay, so this is actually a subspace of w. Turns out this is very important because this range of t is connected to the kernel of t. So we can kind of get information back and forth between these two subspaces. This is the set of all possible outputs. Now, for the question you really want to know, how do you find it? How do you find the range of t? Here's how. Because nobody wants to transform every vector in V. How many vectors are there in capital? How many quadratic polynomials are there? Infinitely many. You'll spend the rest of your life trying to transform all of those. You don't want to do that, right? So there's a shortcut.
Find the span
It's the span of...
of the transformation.
Did you watch my video?
I did.
Oh, good. That's how you... awesome. Yeah, you transform... Okay, I'll write it down first, then I'll explain what I mean. You transform v1, v2, up to vn. You transform those n vectors. You transform those n vectors. That's exactly what you do. And what are those n vectors? So where v1, v2, up to vn is a basis for v. Okay. So the idea, gang, is that you choose a basis for v. You can choose any basis you want. I would just choose the nicest one that you know. So choose a basis for v. So you can be thinking about it. What basis would you choose here? You choose a basis for v, and then you transform each of those basis vectors. Make a list, and then put the span of that list. Yeah. So that's it. Okay, so maybe we should try it out on our example over here. Okay? Let's try it out on our example. Is everybody comfortable with the definition? Oh, I know what I was going to... I knew there was something I meant to say. I keep forgetting. The range of t is the span of something, so it's a subspace. If you had any doubts that it was a subspace, they should have stopped the minute you saw me write span of something, because whenever you take the span of any set of vectors whatsoever, you are making a subspace. Okay, so this is going to be a subspace, and here's how you calculate it. You literally just transform each of your basis vectors. Okay, so here's my question. What basis for, so I want to go back to this example, number 5. What basis do you want to use for P2 of R? This is not a hard one. Basis for P2 of R. Anybody?
1x squared.
Thank you. Yep, that's the standard basis. That's the one we should always just think of using. Okay? Just the powers of x. Okay. Good enough? So I have to transform 3 vectors here. So I have to take t of 1, then I have to take t of x, and then I have to take t of x squared. I have to calculate these things. Actually, I think we already have these values from earlier in the problem. You know what? Let's pretend we don't know the values. Okay? Because sometimes people, for some reason, they have a hard time evaluating this, so I want to practice it. Here is my formula right here. Let's just do it from this formula. So if I want to evaluate t of 1 using this equation here, how do I do it?
plug in 1 for C and 0 for A and B.
Exactly. You put in 1 for C and 0 for B and 0 for A. Right? So if I put a 1 everywhere I see a C and I put a 0 for everywhere I see an A and a B, I'll find my answer. So it looks like it's going to be -1 and then 2 and then 0 and then 0, which is probably the matrix we had written down originally for what T of 1 was. We're just getting it again. Make sense, guys?
Mhm.
Yeah, right?
Did you say that again? I just missed.
What we did is what we're doing here, we're not plugging in, oh, this is important, we're not plugging in a number for x. We're plugging in numbers for A, B, and C, which will give me the value of the polynomial I'm interested in evaluating. Right now I want to evaluate T of 1. So to do that I have to put a 1 for C, a 0 for B, and a 0 for A, so that this thing in parentheses just becomes 1. And then I can take T of 1. So if I put in 0 and 0 and 1 for A, B, and C, I'm going to get that matrix that we just wrote down right there. Clear enough? All right, how about T of x? How am I going to find out what T of x is?
Put in a 1.
Exactly. Put 1 for B and 0 for A and C. So if I put in a 1 for B and a 0 for A and C, what am I going to get? I'm going to get -2, -2, 2, and 1. Okay? And then how am I going to get T of x squared? Put in a 1 for A, right? So if I put in a 1 for A and a 0 for everything else, I'm going to get 6, -2, -2, and 0. Does that make sense? Okay. So now we've got, I think I'm going to erase this now. We've got what we need out of this one. So we have the range of T then. So here you go. What is the range of T? The range of T is the span of those three matrices. Right? If you believe my definition over there. It's just the range, it's just the span of the transformed vectors that we just computed. So -1, 2, 0, 0, comma, -2, -2, 2, 1, comma, 6, -2, -2, 0. It's that. Okay. Let me ask you another question. What is the dimension of the range of T?
3.
Yeah, 4.
You know, the right answer to that question is 3.
We got lucky.
But you answered it very fast, so I want to know, why do you say 3?
Counted the 3 matrices.
Okay. You guys buy their logic? They're saying it's 3-dimensional because there's 3 things in this list.
No, because there's 3 ABs.
There's 3 variables. The fact that there's 3 variables actually comes really from the fact that this was 3-dimensional here. The V was actually 3-dimensional. So we got these 3 variables, but I would be a little nervous about it. You seem nervous about
Oh,
it.
you have to put it in. Yeah.
Exactly. Exactly. It's the usual issue. I have a list of vectors. I know that they will span whatever they span. That's fine. They span the range of T by definition. But are they Li or LD? Sort of have to check that. So what you'd have to do then is the usual thing. Put these guys into the column. There's the first column, right? Second matrix in the second column. And third matrix in the third column. Right? Augment it with a 0 vector and do your EROs. It turns out you're going to be right. You're going to get 3 pivots. Just ignore for that part. You're going to get 3 pivots, no free variables. No free variables is a good thing. It means they are Li. So they are linearly independent and they span the space. So here is a basis for the range of T, and it's 3-dimensional. Now can I tell you something really cool? Although this isn't something I'm requiring you to know, but I'm just going to tell it to you anyway. Because it just is awesome. the dimension of the kernel plus the dimension of the range. Okay. Let's go back to the situation. We're not sure what it is yet. Okay, the dimension of the kernel plus the dimension of the range. This is really neat. I'm going to write it here. You can use this anytime you want. Turns out it adds up to the dimension of V. Always the dimension of the input vector space V, which in this case was 3. So here's the deal. This is a 3. We know that ahead of time, right? We did a whole lot of work earlier to find that the kernel was trivial. So we actually know, oh, this is amazing, we actually know that the range is 3-dimensional just from this math right here. Which actually means that without doing this ERO process, we actually know already, if you know that fact, we already know that these are LI. Because if they were LD, we'd be throwing one of them away and getting a smaller set, which would only be a 2-dimensional or a 1-dimensional range, and the math wouldn't add up here. So you actually can prove the LI part through this current. This is what I was saying at the beginning of chapter 5 about how transformations between two vector spaces help you understand those vector spaces better. The fact that these are Li kind of comes from knowing, having already done the kernel and knowing the dimension of V, even though these are not even vectors in V. They're in W, right? Now, you don't have to know that. You can just think of it as, well, we have to test these for linear independence, put them in the columns, and you see that there's no pivots there. Or there's no...
Would that be an acceptable way to answer that, though? Would be
Yeah, you can use it. You can use this. I'll mention it tomorrow as well. I'll probably get pretty excited about it. I love this result because it really does mean that you can answer questions that would have been a chapter 4 question. Are these three matrices Li or LD? We suddenly we're in a better position to answer that question simply because we have a linear transformation sort of in place so that we have this tool available to us. It's incredible. So, anyway. Everybody all right with that example? It's a lot of stuff there. I know some of it's kind of newish, but it's all just meant to help you out. Hopefully it fits together better. All right, let's do number 6. The next problem is also on linear transformation. The one thing I'm not going to have a lot of in this review session is probably the Gram-Schmidt stuff, kind of the orthogonal, orthonormal stuff, just because that's so computational, and I think there's enough of it in other places. I really would rather focus on the linear transformations. So here's number 6. I'm going to take T from P2 of R to P2 of R, and here's the formula. T of P of X is X times P prime of X plus 2 times P double prime of X. Okay? And there are several parts here. I want to show that it's linear. I want to find a basis for the kernel and find a basis for the range. So if I want to show that T is linear, what do I have to do?
See if T respects addition and scalar multiplication.
Exactly. T has to respect addition and scalar multiplication. Now, this is a polynomial in P2 of R. So would you recommend that I rewrite it like this form?
Yeah.
No.
You know, it's an interesting question. Which would be easier? Would it be easier to deal with P of X and Q of X, or would it be easier to deal with AX squared plus BX plus C and dx squared plus ex plus f. Which would you rather do?
P of
Q,
x.
X, and Q.
P and Q, right. For the purposes of showing that this is linear, we are actually better off just leaving it in this abstract format. Okay, so, but as you're going to see, when we want to find the kernel and the range, the abstract format is not going to be so good. So it depends on what you're actually trying to do. For just showing the linearity part, I'm happy just leaving it the way it is. So let's do that first. That's part A. Show that this is linear. So T respects addition. This is the first. This is always a sort of a two-step process. Yeah, Aaron, what's up?
Just to make sure, this is the axioms
For linear transformation.
not the inner vector spaces, right?
No, we're not doing inner products. We're not doing vector spaces. This is transformation. It's actually not even an axiom. It's really just
Oh, right.
it's just a definition. Yeah. Okay, so how do I do T respects addition?
T
How do I start it off?
times B. T of P of x plus Q of x.
Exactly. So we take P of x plus Q of x. We add them together. Okay. And of course, adding them together, see, if you had written ax squared plus bx plus c and dx squared plus ex plus f, then you'd actually have to add them together and like group the terms together, and you'd already be writing a bunch of stuff down. Here, there's nothing else to really do. You just leave it as is, and you go straight to t of this expression. So the answer is, it is x times the derivative of p of x plus q of x plus 2 times the double derivative of p of x plus q of x. Okay, so you just, everywhere you see a p of x in the original formula, you just put p of x plus q of x. Okay, what am I going to do from there?
Take the derivatives.
Yeah, basically,
You guys gotta take the derivative, put P prime of X.
yeah, just put the prime with each of the polynomials, right? Basically, it's just going to be x times p prime of x plus x times q prime of x. We're not doing a product rule here, by the way. The x is out in front. It's just the derivative of these two, and then I'm distributing the x. Over here, this is just 2 times p double prime of x plus 2 times q double prime of x. Right? And now what would you suggest that I do?
Separate them and then substitute.
Yeah, how to group them in a certain way. I want to eventually, by the way, it might help to remember where we're trying to get to. At the end of this calculation, we'd like to get t of p of x and t of q of x by themselves. So the p and the q should be separated. So the first part is going to be xp prime of x plus 2p double prime of x. We'll put all of the p stuff together. And then we'll have another term where we put all of the q stuff together, right? It'll be something like that, maybe? That look good?
Yeah.
It's actually not that hard. Just kind of follow your nose kind of thing, as my teacher used to say. So you just do the only thing you think you can do, and you end up with the answer you want. Okay. How about the other? What's the other part we have to do?
Multiplication.
Scalar multiplication.
Right, scalar multiplication. So T has to respect scalar multiplication. So let's talk about that. T respects scalar multiplication. So how's that one going to look?
Constant K.
K.
Okay, I have a constant K. I usually like to call K. And what do I need to do with it?
T and then parentheses
Multiply.
K times Q of X.
Okay, good. So I'm going to take a K times P of X and transform that. Okay? So again, we can't really simplify K times P of X. It just is what it is. So we just go right to our formula. We get X times K P of X prime plus 2 times K P of X double prime. Okay? And what can I do with that? Yeah, K is just a constant. The constants come out of derivatives, as you know from your basic calculus courses. So you just take the constant straight out, and we can pretty quickly make quick work of this little problem. Basically, the K comes straight out of everything. factor it out completely, and then the part that's left inside